Hey everyone, thanks for tuning into this week's AM Friday. Today we have Nick and Daniel talking about Eiger, Markforged's 3D printing software. Take it away, guys.
Hello.
Hey, Nick.
Hi.
Thanks, Susie, for introducing us. I'm not sure if, so this is kind of a part two of a two-part AM Friday series. Last week, we kind of talked at a higher level about the software and maybe gave a 2-minute overview at the very end. Today, we're going to talk very briefly about Eiger in a general level and then spend the rest of the time going through a demo and kind of answering user questions about the software as like live and as quickly as we can.
Yeah, so last week we covered how 3D printing software came from basic slicers that worked basically as a liaison between your CAD file and the printer to give explicit instructions on how to print parts. And that involved a lot of tinkering with the printer to get successful parts and was a lot of low-level instructions that you gave to the printer. And we talked a little bit about how that has evolved over time into softwares that have a lot more features, involve a lot less tinkering, and are starting to scale up towards manufacturing tools.
Yeah. So if you want to go check that out, if you haven't, feel free to check that out after this. This is still going to be a live demo. It should be pretty informative regardless of whether or not you saw that. So, but if you're interested in kind of that higher level view, go and do that. We generally give updates at the beginning of these. We have one update, which is I'll let Nick announce because he worked on it a bunch.
Yeah, so we've launched a whole new set of applications web pages on our website. So if you go to markforged.com/applications, we've launched about 10 new web pages, and really the idea is that it breaks down the applications of 3D printing with Markforged printers throughout the entire product development cycle. So as we know, 3D printing really started off as just a prototyping tool. And so yes, you can use our printers for initial prototyping, but it really goes through functional prototyping, through the entire tooling process, the manufacturing process, your assembly line, all the way through end-use parts. And so it really helps map out how you can use our printers through that entire manufacturing product development cycle. So if you want to check that out, markforged.com/applications.
Yeah, and I think it's really interesting because when we first think about 3D printing and applications, we usually think of, can it work for this specific part, these kind of disparate applications. And so we're trying to kind of talk about here, and I think we'll probably spend an AM Friday talking a bit more in detail about how we consider this and the way we go through it, but is if I develop a product, where does 3D printing fit in? And we're trying to answer that question instead of, will 3D printing work for my application? Because what we find is that when people buy our printers, often they purchase the printer with one application in mind, and then they realize it helps in various different parts of the organization. Good example of that is one of our customers, Humanetics, who makes crash test dummies, bought it because they thought they could print ribs for the crash test dummies, which ended up working. So their base value prop worked, and then they realized that they could that the more valuable value prop in the long run was actually printing thermoset molds. And so it's like basically completely reevaluated how they looked at it. So real interesting stuff. Would recommend taking a look. It won't take too long to get through. Nick did a great job with it. Yeah, and so I guess now let's talk for about 2 seconds about literally what is Eiger, and then we'll get to demo.
Yeah, so Eiger is Markforged's 3D printing software. It's a cloud-based platform, meaning that you can, that's a buzzword we hear a lot, cloud-based. Basically what that means is anywhere where you have an internet connection, you can access it and use it just as if you were connected directly to the printer. Yeah. And so the idea is on a base level, like how 3D printing software started, it's a slicer. So it helps you turn parts from STLs into printed parts. But there's a lot more features that we're going to be talking about today that really bring it to this industrial production level front where you're actually using it as a manufacturing tool like we're talking about, which includes part management and fleet/printer management.
Yep, and yeah, so basically we split Eiger into 2 or 3 kind of sub things. The first one is obviously the slicer, as Nick mentioned. The second one is a part management system. So a way to keep parts that you're 3D printing all together on the cloud to manage them as such in folders and save builds, do versioning, that kind of stuff. And then the last one is a printer or fleet management system. And that means basically if we always say we have 100-something printers here, how do we manage the entire fleet? How do we see how things are going? What's printing, what's not, what's available to print on? Basically anything along those lines.
Yeah, and how do you make sure that you're utilizing as much bandwidth as possible on your printer so they're not sitting idly while you have parts waiting in the queue?
And so the slicer part is the part that kind of everyone kind of assumes is the true part, and the other things are kind of what differentiates a slicing software from a quality 3D printing enterprise scale software. Yeah, I think with that, let's just get to the demo. Let me switch screens, and then we can share my screen. Are we good? Oh, I can see it. Perfect. You can just bring up the outline full.
Yeah.
All right, perfect. So okay, so this is Eiger. Eiger is basically, as we said, it starts in a pretty simple like folder-based view. So here we have this is the base view of this tutorials Eiger account that we have. It's on our base Eiger org, and we can see there's a few different things here. We have parts. So this part's just sitting in the kind of the base folder in our overall library, and then we have projects themselves. And projects are really good tools you can use to kind of organize parts as basically as you vector along projects.
Yeah, and so rather than keeping files organized within your own file system, whether it's on your computer or on Google Drive, and having these collections of STL files, you can actually organize it directly inside of Eiger. So that's where this part management idea really comes up.
Yeah, so here's an example. So Alex, one of our fellow engineers here, did a really interesting talk on designing for printing and kind of how to route fiber effectively. And so to do that, he basically created these 5 example parts, some of which we'll kind of talk about today in demoing Eiger. He was able to store them in a folder here. We have other ones here where there's an overview. We have just some typical Markforged parts to talk about. And that way you can kind of organize by project. I've seen places that run a more significant printing organization have like 100 projects that they kind of name code and then co-manage in a Google Sheets or Excel file as well. So yeah. It's basically a relatively scalable way to manage what parts you have. And it kind of breaks the base concept where you basically, there's no concept of a print file. The print file is interfaced directly with the software, so you can change it and do stuff dynamically.
And this also makes ease of collaboration a lot better, because if Daniel has a project in Eiger that has 10 parts in it that he's been working on for a specific project, and I find that I need to print one of those parts, I can go into Eiger, and there's a drop-down menu that.
Yep. So Nick sliced this part, and I'm not. This is my account. So you can see if I wanted to clone this part and make it my own, I could.
Yeah.
So that's a nice, easy way to say, okay, we're looking to make this part. The whole org can see the part, and here's the kind of the easy way to clone it and get moving on your own.
Yeah. So if I see a part that Daniel's printed, this has actually happened before. Like, oh, I see a part that one of my coworkers has printed, and on our Eiger organization, I'm like, oh, I'll just go find it on Eiger, and I can search it on Eiger and print it myself. So it really brings up this idea of collaboration and being able to organize it efficiently into specific projects.
Yeah. So with that, I think we're going to go and just talk about like the actual meat of the slicer itself first. And I guess Devin just wanted to say, Eiger's free to use. I will say that it's free to try, it's free to use. So if you don't have a printer, you can still try it out. I think you can slice up to about 30 parts without a printer and just see how it works. Our slicing software doesn't work with other printers, so it's not like a simplified 3D or one of those type of softwares where you can basically just output G code that you could then put into a different machine. It's not how it works. It works just with our printers, but if you want to try it out, if you're interested in buying, if you want to see how the fiber stuff works, especially after this, feel free, and you can definitely try some stuff out. It's fully functional aside from the printing. So yeah, with that, I guess we're gonna go and look at this alignment bracket. So Nick, you want to give the kind of the basic ones and twos of this and talk about just the basic part view?
Yeah, so this is what we call the part view. This is what happens after you input the STL into Eiger. And so you can orient the part much like you may have seen in other slicers, where if you want to rotate, you can do this sort of manual rotation thing, which is like pretty basic for some different slicing softwares. But additionally, one thing that I really like about Eiger is that you can click the face to make it flush to the bed. And so this is a really useful tool, because instead of having to rotate and move the part around manually, you can literally just click the part that you want flush to the bed, and it will automatically do that for you.
Yep. And with that, so this part is not a perfect example of that, because this part's pretty obvious what print face you're working with.
Yeah.
But if you're trying to print a part that's more uniquely shaped per se, figuring out the flattest place to mate it to the bed is often a good thing. It works really well if you happen to have not designed a part for 3D printing, so you don't have a clear build face in mind. You can kind of experiment and see what the different aspects are. Within that, you can see another cool thing within the parts view is you can see the material estimations, the size, your cost, and how much plastic and how much fiber you're using. So Alex, when he sliced this originally, put a bunch of fiber in this part. So this part costs about $100 as a whole. It weighs 1/4 pound or 106 grams. It'd take a little less than a data print, 2/3 of a data print, and it's 150 by 100 by 30, so about 6 inches by 4 inches by an inch.
Yeah, so as we'll see when we go into the internal view a little later, this part is actually packed with continuous carbon fibers, which is why it runs a little heavier and a little more expensive. And so you can see on the right, this is basically where you toggle what materials you want to print out of. So onyx is our base thermoplastic material for our composite parts. And then you can choose your continuous fiber over on this side if you want that extra strength to reinforce it with. This one will be reinforced with carbon fiber. And then you choose which printer you want to print it on. So we're not going to do it on the metal series because it's a composite part. And this is able to be printed on our desktop series Mark II. And so these are like the basic management of from like a high level of like your materials and what type of printer you're printing.
Yep. So at a base level here, I see a couple of questions or comments saying, oh, it's proprietary, bummer, a couple of things along that. I will say this. So the idea of having a non-proprietary slicer is basically that your slicer basically export G code and then and you'll basically be able to modulate settings and change stuff and use whatever printer you're working with. It's just like fun. If you go in and talk, kind of look through our previous AM Friday, we kind of differentiate that from what we're trying to do here, which is a more industrial-based system. And the core of this is that because no one else prints with continuous fiber, a slicer like this would be relatively useless for anyone who's not using one of our printers. And so the software comes with a printer. It's not, it costs extra. You can still use it and you can try it out before. But from like a utility perspective, it would not be super useful if I say try to print something like this on a Prusa.
It goes along with the balance we talked about last week, which is making a software specialized for your process and then making it more usable across multiple platforms. And so Eiger is more specialized to our specific processes.
Yeah, would recommend. I think Simplified 3D is a really good one for if you're looking for that. They have a bunch of profiles for printers already, and then you can modulate settings. So that if you're looking in that respect, definitely would look there. So yeah, and so then within this, you can see part settings and you can see material settings and all kind of these basic stuff in the part view. So the part view is basically where you're laying out your part and just doing the basic things. So defining your base materials, your base reinforcement, what kind of printer you're putting it on, doing an orientation to make sure it'll print. You can do a few more things in the part settings, like you can use brims or expand thin features if you're looking, if you have a kind of interesting parts. Brims are good for parts you think might warp. That's pretty rare, but they might. Raising a part is really good if you have a part that's a complex shape. And so you don't want just one tiny face to be made into the build plate, so you can kind of raise it up a bit, and it'll print all on supports. So that's an interesting feature. You can change units and you can change the scale, which are nice. You'll notice here that in this case, the layer height is locked. The reason that the layer height is locked here is because we're using fiber. So if I were to shift this to no fiber, I could change the layer height to one of our three settings, which are 100 microns, 125 microns, or 200 microns. The 225 microns is unique. You can print it with it in plastic. The reason it exists in the field of the other ones is that carbon fiber uniquely prints at 125 microns. It's just the size of the fibers. So here, let's see what else we have here. Oh, we can go. So in the material settings, so we usually don't mess with these. You can mess with these if you want those. So if you want to have a solid fill part, you can basically change this and change the type of fill. Our default fill is basically triangles inside the part. You can change it to hexagons or squares or rectangles. You can change the fill density. It's default at 37%, which is basically just the amount that the calculation we backed out from volumetrically from our infill. And then the wall layers we set at 2. So that's basically along the outsides of the part, how many passes is it going to do. 2 is our base. You can go down to 1 if you want to print really thin walled parts, or you can go up to 4. I will say that wall layers walls, roofs, and floors contribute more to our print time than anything else. So if you're really trying to do something quick and dirty, you would do something where one of the quickest ways you could kind of decrease print time is decreasing a wall and a floor layer. But that does compromise quality. Yeah, and then the fiber layers. Nick, do you want to talk a bit about the fiber?
Sure.
For the reinforcement settings on the part view?
Yeah, so reinforcement settings on part view, if I'm going to be honest, I like using internal view more, but you can get a really high level view here where, so we have this toggle that says preserve custom fiber that because we've gone into the internal view and saved them. But here, basically what will happen is if you can choose the number of fiber layers you want and the type of fiber fill that you want, which we'll talk a little bit about in a bit, and then it will create a sandwich panel on the part automatically. So this is useful if you're gonna have a part that's oriented on the bed this way and will be in bending. But if you want a more unique or custom fiber fill, then what you would do is you would go into the internal view, which is down at the bottom right of this window.
Yep. So we'll check it out now. So the kind of the part view is pretty similar to most other printing softwares. They have something of that type. The internal view is a bit more unique. So what you look here and you can see is this is a 3-dimensional internal view of the part itself. So what you're seeing is a few things. One, you're seeing kind of this like ghosted shape overall of the part, and then 2, you're seeing a bunch of blue. What the blue is the continuous fiber reinforcement. So if I go in here, I can see what's visible, and I can get rid of the concentric and isotropic fiber fill, and that will show this is what the part looks like kind of as a ghosted view in terms of actual print paths without the fiber. And so then we can add in the isotropic, which we've used kind of in this bottom panel to add strength, and then we can add in the concentric, which we've used in the rest of the part to add basically a wall on the outside of the part, and check that out. The really interesting thing here is if you look at, so visibility, you don't really need to mess with too much. It just kind of can show you what's going on. We remove the triangular fill by default, but you can see this has that triangular infill inside the part. If I were to pan this part up, you can then see the triangles really well. So this is this easily movable dynamic view of kind of the 3-dimensional part. And this histogram is really cool as well, right, Nick?
Yeah, and so this is actually my favorite part of the internal view. So in the 3-dimensional view, you can click on different sections, and it picks groupings of layers of the sliced part. And then you can choose within that what type of fiber fill you want, or fiber layout you want in that section, and how you want it reinforced and with how much fiber. So that's really cool in the 3-dimensional view, but you can do that. But also what you can do is you can go into the 2-dimensional view. And so what this allows you to do is to go on a single layer granularity and go throughout the entire part to see how the part is sliced.
Yep. And so 3D kind of shows you the overall view and allows you to create the groupings. So the reason we kind of brushed over doing the showing the fiber view in the part view is because it's a kind of a really good intro, and it's a base thing. But when we reinforce parts with fiber, we just toggle the fiber on and then slice it and then go into the internal view and change stuff. So if you want to go back to the 3D view, Nick.
Yep.
So as we said, we can change fiber groupings here. So I'll take the mouse. We can look here. This is a large fiber group, and you can see within this group, which is basically all of these layers here, this slice of the part. You can see then if I change this to a different group, it shows a different set of layers. Oh man, there we go. And then go back to this main group here. Wow, it's not doing it right now. There we go. So we see this group, and we see that it's set with this basically a series of settings, which are concentric fiber, all walls, and 2 rings. I could change this right now, and it would dynamically update. So let's say I want to add an extra ring of fiber. You'll see it'll go back into the loading screen a bit, and it should dynamically add the fiber here. You can see it as the histogram is recovering, showing that it's adding more. So you can see here now, if we go into the 2D view from this same thing, we see now three loops of fiber on the inside instead of 2. So nice, easy way to dynamically update groups. One other really interesting thing about this histogram is it actually shows how much fiber is being used per layer, and that's normalized to the layer that's using the most. So if we look here, this is kind of an uninteresting histogram because these 2 layers are all isotropic, and isotropic basically fills the entire layer with fiber, and as a result, that means that it's going to have the most fiber by a pretty wide margin. So if you look here, these are basically entirely filled with fiber, whereas these have 1 or 2 loops. But we can change that if we want. We can go in here and let's create a smaller group in here where we go and create a new group, and we could add, say, I don't know, 7 rings of concentric fiber, add a lot more, and you'll see now that these have more fiber inside the part, and they've dynamically updated. So that's a good way to kind of see overall where your fiber usage is. We talk about kind of fiber reinforcing techniques in other webinars, but this is a kind of a base view of how you implement them.
Yeah, and so we've mentioned isotropic and concentric fiber a lot. And what we mean by that is if we go to this grouping here, and you can see that the fiber is routed, the blue represents the carbon fiber, it's routed all along the perimeter of the part and around the perimeter of the holes in the part. And so this is called concentric because it's around the edges. And this is really useful if the part, so what this is going to do is it's going to resist bending in this direction. And so concentric fiber is a really good way to offer a lot of strength in your part while making sure you're preserving the amount of fiber that you're using, so without using a ton of fiber. But when you need a section of the part to be really strong and you really need to fill it with fiber, what you can do is you can use our isotropic fill. And what that does is it does a couple rings around and then basically alternates the angle at which it lays the fiber and fills in the rest of the area of the part. And the reason that the angle alternates is to give it that quasi-isotropic strength.
Yep, and that alternation, if we go back to the 3-dimensional view, is automatic. but it's also changeable. So if I go here and I click the whole group, there we go. So I click this whole group. This is this stuff that I'm just highlighting in the top right is actually showing basically the alternated degrees. But if I want to change this and have only 3 degrees that I do, I could do 0, 60, 120. And that will reslice all of those layers and have those that basically 3-step alternation instead of the 4-step. It might take a second, but now it's done. So if you go in here now and we look at this fiber, now instead of doing 45, 90, 135, 180, which is basically a 4-step kind of spin, now it's doing a 3-step spin. So, and that's something you can do dynamically. You can also go into the same thing and say you want a lot of fiber oriented in the same way. I could just make it 0. Or if I was feeling special, I could make it like 56 with some random number. And the fiber will basically orient based on that kind of cardinal direction the STL is oriented as.
And so we've got a couple of questions that we'll answer as we go. Yep. One was, can you add color? All our parts are, so Onyx is black, but you can paint it. So if you are looking to get different colors, they are paintable.
Yep. And also, just a note, feel free to ask questions during this. We're just kind of going through the features of this software that are kind of unique and useful to talk about. And so if you have any questions to clarify, this is kind of it's a rather broad, expensive piece of software. So we're kind of giving a basic overview. If you want to kind of ask a specific question, we're happy to go in and answer that. Also, so someone asked what our largest build volume is. It's 330 millimeters by 270 millimeters by 210 millimeters, which in standard is 13 by 10 by 9 inches. So we don't make giant printers. The calling card of our machines is that they reinforce parts with fiber or they're metal printers.
Yeah, so depending on how big your parts are, you making larger tools and end-use parts are possible, but it really depends on what scale you're talking about. One thing that we do have customers do is make assemblies for example, for a sandcast that actually we've just made, making sandcast cores, a mold, printing multiple parts and then linking them together into making a larger tool. So you can definitely bypass that volume constraint.
Someone asked if you can add more layers out from the holes for tapping. You can. We actually have a whole series of design webinar. Whole series. Basically, we have a kind of additive design focused webinar that's only focused on threads. We don't actually recommend tapping our parts because it's basically just tapping plastic. In answer to your question, yes, you can. So if I were to go in here and save this and then go back to the part view, the setting I would change here is not the fiber setting. I would change the plastic setting. So I would add more wall layers here. You can add it to 4 walls, and that makes it a little easier to tap. But generally, what we recommend when we're talking about tapping is we recommend basically using heat set inserts. And I'm not going to go too deep into that, but there's basically we have a whole kind of study we've done on that and talking about what works best for printing and doing both like quantitative and kind of qualitative analysis of that. So would recommend that.
Yep, for sure. And you can find that on our website.
Yep. Someone in the middle asked, you have an agent in the UK where you can see equipment. Yes, we definitely do. If you go to our website and do the contact us or request a demo and just say that you're in the UK and love to see it, we can connect you with a reseller or basically a value-added partner out there. So with that, so this is kind of a base fiber view going through that. Once you kind of have decided on your fiber, and you see here the same print time and cost estimations are here, you can go to print, and when you go to print, what it does is it basically changes from the fiber view to laying it out in an actual print bed or on our machine. So in this case, this is the Mark II. The cool thing here is that I could also, even though I sliced this with the Mark II in mind, I could also print this on the X7. Same thing works here. So you can see it in the actual build as well. So if I wanted to, say, add more than one part here, if I'm on the industrial series, I can move this around on the build plate. So this is determining where it prints. You can basically spin it around if you so desire. The other thing you can do here is add another part. So let's say I want to print 2 of these instead of 1. I can print another, and I can make sure that they're oriented correctly. We do this all the time with our sample parts. Actually, there's another feature that's pretty interesting where if you click it, if you add a bunch of feature, you add the same part a bunch of times, it'll kind of auto space it for you. I try to like tweak things manually because I'm a little bit, I'm kind of crazy like that. But you can also do things like if you want something to print, be more space efficient, turn it around by turning that around and then having them interweave here. It'll obviously tell you if your part conflicts. But here I could print parts like this, and then I could basically have a bunch of them on the build plate at once.
And this is where the estimated print time really comes in handy because you can see, so we also have some learned content on our website about how you manage printers and your bandwidth. So making prints happen in units of time of when you're in or out of the office is really helpful. For example, if you're leaving work and you want a print to be done by the time you get there the next morning, it might be good to kick off like a 15-hour print, because that way, right when you get back, the print finishes and you can kick off another print and not waste bandwidth.
Yep.
So if you want to load this bed up and make it a multiple of 8, usually is pretty good, of 8 hours, you can add parts, and then you can add like these smaller parts into it as well. And
probably the carbon fiber one, because that'll work.
Yeah, this one.
Yep.
So you can add these parts, and then you can get, so for example, this would be 1 day and 22 hours. So if I'm leaving for the weekend on Friday night, for example, I might make something that's like, I might add one more, and then so I leave for the weekend on Friday, and then by the time I get in on Monday, my print's done, and I haven't wasted any. It hasn't finished early, and I haven't wasted any printer bandwidth.
Yep.
So this is a really good way to experiment with that.
Yeah, and so the only thing that constrains you on a build is a printer basically has to use the same plastic, the same fiber, or no fiber at all, and have the same layer height. So because it basically, when you have a build, it takes it and does discrete layers. But within that, you can print whatever. So you can print big batches of stuff. You can print multiple parts if you want. A bunch of different stuff. I see we have a few questions here. So first one, Theo asks, can you export a text or CSV file with a breakdown of the part composite specs for easier reference and A/B part testing? I don't think you can export a CSV of that stuff. There's only about four specs you can see, so you can just kind of take them down. But that is definitely something that would be a good idea or for a feature at some point. Someone asked, can you, when orienting fiber direction from a different slice level, can you work from measurements, e.g. having 0 to 90, 10 millimeter height from base? So let's go back to our, oh no, I'm on a different.
That's a great question, yeah.
It's an awesome question.
We didn't really cover that.
Great question. Here we go. All right, so you go here. So if you look here, anywhere in this, the answer is like a soft yes, basically, I would say, because what you're doing here is, you can see the layer number is clear. So right now I'm editing layers 28 to 44. And
also on the right side, you can see
just there you go.
The depth of the part here. So if you're looking to, let's say you want to, you said 10 millimeters from the base, all you would have to do is, I find it easier to do in 2D mode. You just find the layer that's 10 millimeters from the base, which would be right here. And then you know that you can make a fiber section starting from here.
Roughly,
and go extend as far as you want, and then orient the fiber using the settings that we just mentioned. So it gives you those measurements at the bottom.
Yep. And so and I was normally saying you can go by layers, but layers vary in height. And the only other thing is that it would be, it doesn't like explicitly say it in the histogram. So as an exercise, you have to go find it. But otherwise, yes, you can do that. And the other thing we'll see is that you kind of reinforce unique features. So in this reinforcement here, the reason that this is done isotropically is because we want to reinforce, it's easier to see in the part view, we want to reinforce basically this top surface here of this bracket because we believe it's going to be bent. So we're basically creating a sandwich panel on the bottom face here and the top face. And what that's doing is basically making this part of that bracket super strong. The other part is fiber reinforced with concentric fiber, but the top and bottom here are critical. So if we go back in here, that's why this grouping of layers here, which is the top 5 layers of this of kind of that fork, are reinforced with isotropic fiber. So that's why I added that region here. So that was another example where we're looking at a specific feature of the part to reinforce extra.
Yep. So the next question says, FDM or FFF requires orientation for strength. With continuous fiber, is that necessary? That's a good question. So anytime that you're going to be depositing material layer by layer, basically every time you have an FFF type process, you're going to have some sort of anisotropy in your part. And that's because the adhesion between layers is not always going to be as strong as the adhesion of a continuous strand of an extruded material. And so that is true with fiber composites. And so that is something to keep in mind when you design for 3D printing and when you're laying your fibers, that fibers are always going to be, by the nature of a fiber, first off, stronger in tension. And second off, they're always going to be stronger bending along the axis of a fiber rather than between layers of a fiber. And so this is something that can be solved whether in your print orientation or in your assembly, depending on how you're using the part.
Yep, and I would say definitely that your point is true, and it rings even truer with the fiber because the fiber parts are even more anisotropic than your typical 3D printed part because you're really reinforcing 2 axes in a serious way, and you're leaving the third. The z-axis tension will not change. Can layer height be changed throughout prints? Right now, no. That may well come in the future. So the thing we will have, so the reason that we don't have it right now is basically the fiber itself is basically is a fiber coated in a plastic. So unlike the plastic material, which can basically be printed at a wide variety of layer heights, the fiber itself that gives the part its strength has to be locked. So at some point, for kind of print speed, it might be logical for us to do something along the lines of have some, like the fiber layers at some layer height and the plastic layers at a different one. Right now, it's locked to the same layer height. It keeps it pretty simple. But that may well change in the future. Someone asked, can layer heights be changed throughout prints, e.g. change?
That was one.
Oh no,
that's one you just
that's when I. Oh, the printing macro. Do you want to take that one?
Wait, which one?
The Vincent's question.
Can you set up a print list macro whereby after you print a batch, the software keeps printing that same batch, say 10 more times? Yes, this is something that we're going to cover. So this is what we call builds.
Oh shoot, we can't do it in this one. I can.
And so actually we can show them in production, Eiger, maybe.
Yeah.
But so what you can do is you saw I created a build just a couple minutes ago when I loaded all those parts. I want to load a couple more parts onto that.
Yeah. Well, let me put on the industrial series.
And so, well, what you can do is after you load these parts on, and this is something that you're going to want to repeat multiple times.
Oh no, I did too many. There you go.
You can actually go down to save build on the bottom right.
Yep.
And what that will do is that will save this for the future, so you can print it as many times as you would like.
Yeah, and I saw something else about automatic spacing.
Yeah, right here.
That's if you saw what I just did here when I quickly added 4 parts. It's the answer again is sort of a yes here. We could be better about this, but if you add multiple of the same part, it will basically create things that automatically space it here. Now, personally, I would say this is not the most efficient because obviously there's a lot of wasted gap space here. But you can do that. And so we have our simple parts, if you have seen them, are basically very thin, like popsicle sticks. They're very small. You fit about 24 of them to a bed. And so the way we create the builds is just adding 24 and it'll automatically do that for us.
Yep.
And then the other thing we're going to talk about was queues. So you can save this build and then you can push a number of these builds to what we call print queue on a certain printer. So if you want to have the same printer print parts a bunch of times, you can basically have it set on the print queue and then actuate the print from the printer instead of from the build.
Yeah, and that's something that we'll cover when we go talk more about the fleet view.
Yep, and then let's see. Okay, and then so Saber Tooling asks, sorry, I may have missed this, but the part automatically core out solids? Yes. So when like most slicers, our part takes in an STL, which is basically just a solid body file that's a series of triangles. It doesn't have any information about the CAD or how it's designed or anything like that. It's just a solid body. It then takes that, it basically finds the you orient it, it finds the shell of the part, it assigns roofs and floors, which are basically the tops and bottoms of the part, it assigns the walls of the part, and then it fills everything that's not a roof, a floor, or a wall in with basically triangular infill. And that triangular infill is coring it out. Our unique aspect of this is that we can go in here, back to this thing, and if you look here, what the fiber is actually doing in the 2D view is it's replacing this triangular infill on the edge here. So the triangular infill is this normal stuff here. The fiber then replaces it on this edge. If you have layers that are not reinforced with fiber, you'll see that the triangular infill goes all the way to the outside. So that's kind of the unique part of the Markforged system. One thing I also wanted to note, this part doesn't really have too many supports, but you can see here, these here are just a hint of same material supports that are going through this hole. So if you have a part that needs supports, it will auto-generate them for you. Does Eiger interface with any additive manufacturing execution systems to share part build data? Not at this point, but may well in the future. Let's see. Someone asked, size of machine?
How the size of machine restricts use? Is there plans to increase bed sizes in the near future? I mean, so it would depend really on what bed size you're looking for. So there's kind of, it's a double-edged sword with build size. So you can create, there's a couple different ways you can go, basically. You see these really giant printers that print really, really large parts, like a couple meters. And those printers, they have a lot less fine of a resolution. They're printing really, really tall layer heights. And parts that they're using for industrial applications, they usually post-machine down to the actual shape that they want. You also see machines that are industrial that are around the same size of ours, but like a little bit bigger build plate at a similar resolution. And so what you see happen is something has to give. If you took our build plate, for example, and you wanted to double the build volume, or you wanted to double the dimensions in each direction, what that would do is it would cube the amount of time that it takes to print that part. So a build volume that's twice as big in each direction takes 8 times longer to print. And so it's this balance between part quality, print time, and print size. And so what the happy medium we found is the volume that we have right now, if that makes sense.
Yeah, here, I'm just pulling up a part in our production Eiger so we can show the print stuff.
Yep.
Here we go. So go back to print. So this is, so let's go, ooh, I've got it. All right, so if we go print here, we can change, so if you go here, we can look and we can see basically on this is our big printer view. You can see what printers are, this is kind of our Markforged instance. You can see our printer names, which are usually pretty comically named as you would expect. And so you can pick a printer. These are the available ones. It will tell me probably if this one, which is an application engineering printer, don't call your ex. Great joke, guys. So this one doesn't have the material loaded that I need, but if I want, I can add this build to the queue. And so that would then add this build to that printer queue, so I could go visit that printer and check out basically check out what's going on. And so that's kind of a really basic way to do that. Yeah, so this is a really cool mold that we did, this HumanX mold that we were talking about earlier. But yeah, so that's kind of the basics there. We could also show printing apart, but I want to go and talk the fleet management stuff if we can.
Yep.
So we can go here. So yeah, you want to start off fleet management?
Yeah, so what this view allows you to see is your list of all of your active printers on this instance of Eiger. And so this has listed each of the printers, if it's ready to print, and how long the queue is that it currently has loaded. So the queue won't automatically kick off necessarily. Let's say like a part jumps priority of the part that's in the queue. You can always print ahead of it. So it puts the printers that are ready to print at the top, which means they have a free build plate that you can start printing on. Then below that, it's got printers that either need troubleshooting or printers that are in the middle of a print and how much time is remaining within them. And so we can click on one of these, and it will give you pretty granular information all the way down to like nozzle temperatures, what materials it's printing out of, and exactly how far along in the print is. So this is a print by our coworker Alex, and I think this is more parts for his BattleBot. And so you can see that it's got about a day left. He's got a couple bigger parts on our industrial printer with a lot of fiberglass in them. And so you can see if there was a queue on this printer, you'd be able to check that out at the bottom here. And you can also see the print history. So you can see what parts have been printed on that printer recently and reprint them if necessary.
Yep. So all kinds of super useful features there. Yeah, so that's kind of the basic view there. We don't want to show too much of our instance just in case we show off anything sensitive, say customer parts. So you can see printer views, you can see kind of part views. You also note these icons up here show washers and sintering machines. So this is equipped for the metal printer as well. But yeah, and that's kind of the basics of the software. We wanted to go through, I guess, we want to go through kind of the metal workflow as well, which is much simpler, but is kind of worth talking about. And then feel free to ask as many questions as you want. We'll be happy to stay around for a bit and answer them. So with that, I'm going to switch back to our demo instance.
And so one thing that you'll notice as Daniel is bringing this up is that the metal slicer is a lot more simplistic in terms of the amount of things you can choose to change when compared to the composite slicer.
Yep. And so this is a part that we use as a demo part quite often. It's called a motor mount. If I wanted to add a description, I would say it's a motor mount. If you would want, which is nice, you can change it. It's pretty easy to do. If you want to look at versions of this, I just cloned this from Nick's instance so that I could edit it here because you can't edit someone else's part. You have to basically clone it to get your own position. But if I changed this and made a bunch of versions, I could basically revert from previous ones. So in this case, this part is, we'll go back to part details. You can see the size, the print time, the material cost, and the kind of the metal volume and all that good stuff. Here, we've decided that we want to print in 17.4. The other option would be H13 from the metal perspective. We're sintering it in our furnace, the sinter 1, and we're printing it on the metal X, obviously, because it's a metal part. So you can see, and we have this rotation. A couple things to note. You have your original units, and you have your layer height that's a little more locked on the metal system. Our scale is 1. But we actually basically in Eiger automatically scale the part up. So this part will look on the print bed a little bit bigger than you would maybe expect to see your final part. And the reason is because there's a 17% shrinkage in the process. So we scale up the part by 20%, which the math does work. As it turns out, the shrinkage and the scale up are different values. So that works there. If we save the part actually won't print looking like this this is not what you'll see when you print. So if we go into the internal view of the metal, we'll see what actually happens to make this part. So a few things happen here. So you'll see this is kind of different than composites. There's no fiber inside. it's mostly one material, which is the metal, and then there's this orange material here, which you can see a little bit in this 3D, but we'll see more in the 2D, called ceramic release. But a couple things, so all metal parts have a raft. It makes them easier to handle, makes them easier to work with, and the supports basically are generated as a part of that raft here. So these things here are support material. If I want to go in here and get rid of the support material, there you can see that back to the normal part. And if I want to get rid of, so that's basically the super simple thing. So to print this part, we print kind of this support structure, and then on top of that, we add ceramic release material, and then we print the actual part. And then so if we go into 2D view on the metal, what it allows you to see is kind of what's going on a granular basis. So here we have the raft. So this is basically the bottom raft of the part. The raft is a solid body that's, let's say, about 15 layers high. You see the support 20 layers high. And then the really interesting thing here is this orange, right, Nick?
Yeah, and so that's the ceramic release material that Daniel was just mentioning. And so this is how you remove the part from the raft. So once the part, it gets washed after it gets printed, and then after it is sintered, that ceramic material basically gets incinerated away, and then you can just break the part off of that raft a lot easier. It's like tacked down to it so that it prevents warping while in the sintering oven, and then that ceramic basically magically disappears in the sinter, in the furnace, and then you can break the part off afterwards.
Yep, and if you look here, so this is where the base of that part is getting tacked down to the raft, and then if you look, as we go up this part, if you look closely here, where this is still being supported, you see this kind of single line of ceramic support. That's basically supporting that incline, because this part of the part here is actually the support material, and this part is this is the actual part itself. So if you go in here and get rid of support material, you'll see that those parts disappear. So that's kind of how the part actually prints. And if we go all the way up to the top here by just dragging, we can then see at some point we'll have these secondary layers where these big flat surfaces are supported as well, and then the rest of the part prints. So that's kind of the core of it. It'll also show you basically your part mass, your final part mass, and your total mass when you're printing. It'll also show you your print time and all those other good features as well.
So we got a couple of questions on H13. Can H13 be printed onto an H13 solid mother block, or does it shrink when sintered? Does H13...
I think it's asking if you can print our H13 onto another
H13 block. So our process is all like an integrated process that's kind of a that is unique. So when you print parts, they're printed on the print bed and then sintered in batches in the sintering furnace. And so while you cannot integrate it into assemblies midway through the process or print it onto assemblies, what you can do is easily create assemblies out of the part. And what you get out of the sintering furnace is just like another H13 part. You can harden it, you can finish it, you can polish it, you can post machine it if you would like. And so in that way, it's like a part made through any other process.
Yeah, there's a couple follow-up. Does it go on hard? I'm assuming the hardness, can it be polished, or is there a sinter finish throughout the part? So few questions there. So one, we have an H13 data sheet. We recommend going to our website, checking on it, or just asking for going to our website and going through the chat, or just any form and asking for information. We can get you all that details and kind of talk about your applications a bit. The other part of that is just the short answer is H13 is pretty hard and it can be hardened. So just a standard, by as printed, I think the hardness is 40. Don't quote me on this exactly. And I think as sintered. And if you harden it, it can go up to 45, I think 46. And that's as we quote by one heat treatment standard. I think there's certain ways to get it higher if you change how you quench it. And then can it be polished? So any of our parts, they're just metal parts when they're done. So you can polish them, or you can post machine them, you can do any of that stuff. The one thing that we'll note is that because our parts, Devin, can you show again? So because our parts have open cell infill, the walls are relatively thin on the part, and we're one thing we're doing now is working to get the part basically variable wall thickness and changing that and making that a changeable feature. But the thickness of the wall here is basically your machinable machinable area. So you can definitely polish it. You wouldn't be able to remove a significant amount of material without kind of blowing through the wall there.
Yeah, and so this brings up the point, if you want to go back to the part view.
Yep.
This brings up the point of, it fits in with our discussion last week, which is slicers before involved a lot of low-level tinkering. And so what we're doing with the metal process is we've chosen settings that allow you to get successful prints repeatably. And so as we keep developing the metal process, since this process is a fairly new 3D printing process, we're going to be able to, this side panel is going to look a lot more like the composite side panel, where you have a lot more options in terms of the number of walls you print, maybe the number of roofs and floors you print, and the layer heights, and everything like that. And so as the technology progresses, the software really progresses with it too.
Someone asked what the maximum wall thickness is before infill has to start. So on metals, I'm not 100%. Is it 800 microns, or is it it's not? No, maybe it's 1600 microns.
I don't know bead width on.
I don't know. I'm not 100% sure what the post sinter bead width on the Metal X is. So but we could give you that information. Just feel free to send us that question, and we can reach back out. So and then the composite side, you can vary it, so you can add more walls. So I think the maximum thickness on a composite one is it's 1.6 millimeters. So that's about 64 thou, so 0.064 inches, I believe.
Yeah, so the idea with metal parts now is post-machining is done to add that extra little bit you need to hit a tolerance on a part that needs to be more precise, and then getting a really nice smooth surface finish on parts that you print.
Yep. Yeah, so it looks like and I'm gonna see if there's any more questions. If anyone has any other questions, it looks like we've gone through most of the base questions we had originally planned to go through. And we've kind of covered the basics. So if anyone has any other questions, so we see a couple more coming in, we can answer those for the next few minutes. Let's see. So can we do two pretty similar? So two questions. One, do you have an FEA analysis process? So right now, we do not have kind of FEA functional for the composite side. The reason is that they're truly composite printers, so that they really do print with two materials. And when you take the solid body that you export from CAD, is really a different part than the part that you're kind of printing. So I think we'll work towards that. It's one of the big things, one of our most commonly asked questions, but we'll definitely get towards there in time.
Yeah, and it was part of our discussion last week as well, is how integrating those different CAD functionalities and tools with slicers. And I think that's really the future of slicers as we'll see it continue to evolve. And what we recommend in terms of parts that you normally would do FEA analysis on is just printing them and testing them, because 3D printing brings a lot easier fabrication. So you can actually print your parts pretty quickly and inexpensively, and then test them in the actual situation rather than running FEA. And that's really the solution for that at this point in time.
Yep, and then a couple others. Can we do topology optimization like end topology? I've never used end topology myself, but we do use Fusion. Fusion has some kind of generative design topology optimization. Actually, there's a part on the Metal X right now that is topology optimized that's right next to us. So yes, it's definitely possible. I would say topology optimization is really interesting because it kind of assumes isotropy, just like most of them do. So it's kind of hand in hand with FEA. So it's not 1,000% accurate right now, just by nature of the process, because the parts we print are not isotropic.
Yeah, so one question about cost. So our printers from desktop series all the way up through our X7, which is our top-end industrial printer, run from $3,500 for our desktop series that prints only Onyx, our thermoplastic, all the way up to the X7, which prints all of our continuous fibers, including and Onyx, our thermoplastic, and that runs about $70,000. And so there's a really wide range depending on what you want your build size and what kind of precision you're looking for.
Yeah, the Metal X system is the cost is about $125,000, but the kind of all in once you realize to get it set up, do all that kind of stuff is like a little bit more than that. It's like maybe in the 160, 170 range. It's a little more expensive, but yeah. So overall, pretty wide range of printers, depending on what you want, depending on what build size you want, depending on the precision you need. The prices kind of vary basically. But yeah, it looks like that's all the questions. I hope we got to your questions. If you have any others, feel free to reach out to us through our website, and we'll try to get back to you and answer them as best we can. But yeah, I hope this was kind of an informative, work through of Eiger. If you have any kind of things you would like to see more specifically, if we want to like kind of accomplish specific goals in Eiger, we'd be happy to show that as well in the future. But yeah, that's all. I think that's all.
If you have things you want to see on future AM Fridays, you can drop it in the comments.
Yeah,
and we'd be happy to. We actually, when we did the X7 walkthrough, that was suggested by one of you guys. So if there's more stuff you want to see, let us know.
Yeah, and I think we'd be remiss if we didn't say if you want to see more of these, we do them every week. Don't forget to subscribe to Markforged on YouTube. Yeah.
Thanks. Have a good weekend.
Yeah.
Thanks for tuning in, everybody. Have a great Friday.